Okay, let's start that over again. Anyways, 2.4. So far we dealt with equations. 2.1 introduced us to equations. That just means it has an equal sign. That's it. And we learned those. Again, still review of Math 61. Finally, we get to inequalities. And now we have these little symbols here. This is the less than symbol. And I think you guys are familiar with that. But there's another property here. It's called the addition property of inequalities. Remember we had the addition property of equalities. Means you can add the same number to both sides, still keep it the same. Now let's see if the sign changes if it's inequality. So, and it says it doesn't. We'll do some example problems from here. So if A is less than B, if I add a number C to both sides, it still is the same exact property. Just out of curiosity here, let's see. Let's go back to pre-algebra just to prove it with some numbers here. So everybody okay? 3 is less than 5? Cool. If I add 4 to both sides, which is the same exact number, everybody good still? I can still keep the exact same property. Okay, and again, since we have a positive case, let's do the same thing here. Let's add a negative number. Let's see what happens here if it's still the same. So how about if I add a negative 10 to both sides, or subtract 10? Will it still be the same? That's my question. 3 minus 10 is negative 7. 5 minus 10 is a negative 5. And what do you guys say? Change the sign or keep it the same? Yeah, negative 7 is still less than negative 5. We're good? Cool. All right, there's the addition property. Remember, we also had another property for equations. It was called the multiplication property. And this one's a little different. If you remember, this is A is less than B. Then we don't change the number if we're multiplying by a positive number. We do change the sign if we are multiplying by a negative number. Let's see how this works out. So everybody okay still? 3 less than 5? Cool. If I were to multiply both sides by 4, the question is, do I still get to keep my inequality the same? Absolutely. Because 12 is less than 20. That's sort of the positive case. I'm multiplying through by a positive number. Okay, how about this one? How about if I multiply through by a negative 4? What happens here? Oh, I got a little problem here because that's going to become a negative 12. That's going to become a negative 20 this time. And here's my little situation. Negative 12 now is greater than negative 20. So in English it says multiplying both sides by an equality by a negative number reverses the sense of the inequalities. So we have to reverse this sign if we divide or multiply through by a negative. Okay, everybody good there? Again, quick review of Math 61 still. But, okay, the new stuff that I probably did not see in Math 61 is this whole concept here. This inequality notation, interval notation. And there's 2 different ways to graph. About 15 years ago, there was a little change. Could you imagine math actually changes? It's kind of weird. So you guys remember open dot, closed dot? Remember that? Okay. Most textbooks are sort of phasing this out. Okay, and then we're going to go to sort of like parentheses or brackets. So basically parentheses are the same thing as open dot. Brackets are the same thing as closed dot. That's really the distinction there, okay? And then at this point also, parentheses open up towards the direction you want to shade in. So notice that little parenthesis sort of opens up towards the left. Bracket now opens up sort of towards the left. On this one where you go greater than, it's a bracket but now sort of facing to the right. Again, parenthesis facing to the right. So it's a little bit different. I'm guessing here. But most likely because this little interval notation right here is very similar to this one right here. So you have notations that are more closer aligned. Okay, so we've got to do a few things here. First of all, something called inequality notation. If you say x is less than 2, the interval for it, and interval, you think of interval going from like the smallest to the greatest. Okay. So if you say I want all the numbers that are less than 2, in interval notation, what that means is you start off at negative infinity and you start going all the way up to positive 2 and you put in a parenthesis. And a parenthesis means you're not including that 2. Okay, good there? Let's go back. Again, got to go through each one of these here just to make sure we got it. And then the graph for it, we're going to use these graphs right here, not the closed dot, open dot. So if you're going to graph it, you're going to put a parenthesis at 2 and then shade down. Cool. All right, how about this one? X is less than or equal to 2. This means I want all the numbers that are less than 2, and I also want that 2 as well as part of my answer. How does that work? We go from negative infinity, you go all the way up to 2, but now you got yourself a little bracket as opposed to a parenthesis. So the graph again, notice the bracket in the bracket. Now I've got a bracket at 2 and then going down. Cool. Let's keep on going. X is greater than or equal to negative 3. If that is the case, if that's the answer that you have, again, notice because of this little equal to part on our inequality, we have ourselves a bracket. We're starting at negative 3 this time, comma, we go all the way up to infinity, and you can't go beyond infinity. I don't care what Buzz Lightyear says. And you're always going to have a parenthesis next to infinity because you can't really get to the last number in the world. We good? It's always going to be a parenthesis, never a bracket next to infinity. Okay, so again, bracket at negative 3, and then you shade off to the right. And x greater than negative 3, that means I just want the numbers that are bigger than negative 3. In this case, I have myself a parenthesis, negative 3, comma, infinity, and again, that little parenthesis there. Again, and notice the same thing here. Parenthesis goes to parenthesis along the graph and goes off to the right. Are we good there? I'll explain that. That's a little new there. So now we can start doing this stuff. So solve the following inequality and write the answer using interval notation. And even beyond that, let's even do a graph as well, just to make sure we got the graph concept here. Here. All right, trying to solve 5x plus 7 greater than 3x minus 9. Let me rewrite it because I don't like the way it's all the way over there in the corner. At this point, just like in equations here, we're trying to get x by itself on one side. So subtract the 3x, that's going to be 2x plus 7 greater than negative 9. How about subtract 7 from both sides? Then again, this is the addition property, right? I can add or subtract any number, still keep it the same. That'd be negative 16. How about divide by 2? And this division is the same thing as the multiplication property, right? Technically, we're multiplying by 1/2 here, multiplying by 1/2 here, and how about x is greater than negative 8? Out of curiosity, show of hands if you got that before I gave you the answer. Hey, okay. Okay, this is called inequality notation, and it says we want to figure out. I'm going to answer it in interval notation. That's the whole point here. So, all right, and let me graph it here. Okay. Let's go to the interval notation first, and then we'll make the graph of it. Even though you can do one or the other, it doesn't matter. So I need x. I need all the numbers that are greater than negative 8. That's what I'm looking for. All numbers greater than negative 8. Including negative 8 or not? No. So we're going to start off with the parenthesis, negative 8, comma, and then again, there's no stopping over here, so we're just going to keep on going, so that means it has to be infinity, and again, always a parenthesis around the infinity. Okay, for the graph itself, because I want you guys to get used to graphing as well, normally what happens is you place a little 0 marker on the graph. You don't necessarily have to do that, but that's sort of customary. Then we find out where negative 8 is. It's all the way over here. And again, negative 8 is where we start, and then we're going to go off to the right. So parenthesis at negative 8, and then you're going to shade in the rest of it like that. And you know the preference in mathematics is that what you do is you make this arrow bigger, so it distinguishes from the arrow over here. So make the arrow bigger, fill it in, and there's your final answer. Let's see, a few things I have to tell you here. Don't make the graph above the number line. It's not above the number line. Some students make it all the way up here, and that's not good. The answer should be right on the number line. You should be shading in the number line itself, not anything above it. Cool, good. I see about 2 erasers happening. All right. All right, another one, all yours. See if you go from beginning to end. Give you a little bit of time there. All right, let's go for it. I'm going to try to do it the 2 most usual ways students do this problem here. So subtract 4x from both sides. Gets you a negative 10x plus 5 greater than or equal to negative 15. Everybody good there? Subtract 5 from both sides. Now it gives you negative 10x is greater than or equal to negative 20. And then we divide through by negative 10 is good. Yep, negative 10 here, negative 10 there. And of course the big alarm goes off in your head, right? We're dividing through by a negative number. We have to switch our inequality right here. And negative 20 divided by negative 10 is just a 2. And usually a question comes up. Oh, let's finish off the answer first here, then we'll handle the question here. Interval notation, let's see, now we're looking at x. I need all the numbers that are less than or equal to 2. Less than or equal to 2. That means I'm going to go from negative infinity, I'm going to go all the way up to a positive 2. And I'm going to stop there. So parenthesis or bracket, what do you guys say? Bracket's good. All right, question comes up. Mr. H, what happens if instead of subtracting 4x, what we did is we added 6x to both sides? The question is, will I still get the same answer? And it's a yes, but let's just sort of look at it here. Again, don't need to do it the second way, as long as you know that's going to happen. The 6x cancels. Left with 5 on that side. Got a 10x minus 15 over here. And we add 15x to both sides. Gets you a 20 is greater than or equal to 10x. Everybody good so far? Divide through by 10. And look at that. Hey, no need to switch our inequality this time, right? Because we're dividing by a positive 10. So that means 2 is greater than or equal to x. And the only question is that still the same answer? I think so. I'll tell you why in just a second here. Whenever we switch numbers, if I were to write the x on this side, I have to switch my inequality. That's the only other time sort of we switch inequalities. And the question is Mr. H, how come? I'll explain. Ready? 3 is less than 5. Everybody agreed there? If I put the 5 on this side and I put the 3 on this side, do I have to switch my inequality? Absolutely. If the numbers switch, the inequality has to switch with it. We good? So there's really 3 different times, right? If you were to multiply through by a negative, if you divide through by a negative, or if you switch the numbers around. So there's 3 different times where we switch inequalities. Okay, but for number 2, even though it doesn't say graph it, I still want you guys to graph this. So can you graph this? Yeah, the question is, if we switched it over like this, is it still this answer? And absolutely, because notice these 2 are exactly the same. Therefore, we're still going to get the same interval notation. And in order to write the interval notation, you got to switch it to here and then go to the interval notation. Anyways, so that variable has to be on the left-hand side in order to read it correctly.
Why do we change the equality sign?
The question, when? Here to here?
The original equality sign was changed and after
right over here, whenever we divide it through by negative. That is from the previous slide. It says this here. If I were to, let me do it differently here. Let's see. Let's say this is 20. 20 is less than 25. Everybody agreed? If I were to divide this guy by negative 5 and this by negative 5, let's see what we get here. 20 divided by negative 5 is 25 divided by negative 5 is. And now the question is, does this get to stay the same, or does it have to switch? Yeah, even according to the pre-algebra rules, right? From pre-algebra, we understand this is the case. So then we generalize it for algebra. It says whenever we multiply through by a negative, divide through by a negative, we have to switch our inequality. Good. Okay. And the graph. Coming up. 0's here. 2 is somewhere here. We go from negative infinity, and it always goes from left to right. Negative infinity all the way up to 2. That means we have a bracket right here. Boom, and then we shade the rest of this over to the left. Keeps on going and going and going and going.
Switch it to the equation to the x in the opposite way, because for mine I did the same thing, I got the same answer, but my 2's on the left side with the bracket and the negative 8, and I still got the same thing.
Alright, so the solution, or the process to get the solution a little more complicated. You got distributive property now, a few other things here, so again, let you guys try it yourself first. Alright, I'm going to get started as well with this one. So distributing the 3 makes it 15x minus 3 minus 7x, and then distributing 3 on that side gives you 3x plus 12. And then collecting as much stuff as we can on each of the sides. So 15 minus 7 right here, these two are here because they're like terms, gives you 8x. Everything else remains the same. And then let's subtract 3x from both sides. Get rid of this right here. It leaves us a 5x on this side. Keep on still working here. You got to add 3 to both sides now. That gets you a 5x is less than 15. And hopefully you guys got an answer of x is less than 3. So interval notation, again, x is less than 3, which means I want to start off negative infinity. Goes up to 3 with a parenthesis this time. Too easy, too easy. And the graph. Finding where 3 is. You don't necessarily have to put the 0. You could put just the 3. That's fine too. So let's see, negative infinity to 3. That means I'm starting with the very, very low numbers. I'm going up to 3, so that means I got a parenthesis. And my graph, let me go back real quick here. It goes off to the left, and again, I got a big O arrow. Let's make that even bigger, and everything else filled in. Okay, good there? Hopefully we're good, because we're going to get into an area probably you did not cover in Math 61 here. So here's new stuff now. Sometimes what we do with these inequalities, we combine them together as sort of two different pieces. And we combine them together as a single piece. And those are called compound inequalities. And so we combine them by some keywords here. We either use a or, so something is bigger than this, or this something is also or smaller than that. So in a sense, it just means that one of them has to be true. Let's see. Gotta go. If we went to In and Out together, and I said, give me either a double-double or a cheeseburger, and you gave me a double-double, are we good? If you gave me just a cheeseburger, are we still okay? Here's a weird one. Ready? If you brought me a double-double and a cheeseburger, are we still okay? Yes, we are, because the or statement just means bring me one or the other, and if you're going to bring me both, you've brought me one of them, right? Okay, so the or statement, that's kind of what it means right here. Sometimes we call it, this is an inclusive or, which means you can have both of them together and it's still okay. All right, then this is called something called union. We're putting things together in terms of union. There's also another thing called intersection. And you think of intersection as where two roads meet, and it's just that piece that's the intersection. And we combine it by and. So again, going back to In and Out. So give me a double-double and fries. You got to give me both, right? Okay. Okay, so let's look at notation and graphing first. So I know this is probably somewhat new. Out of curiosity, raise your hands. How many covered this in Math 61 last semester? Cool. One person. Okay, so this is going to be very new to most people. Let's look at notation first. Let's look at the graphing part first. Then we go ahead. So this is when something starts and it stops, and you have this sort of middle section here. This would be the and statements. And then we look at or statements as we do the examples here. So again, inequality notation, this is a special form here, because you're saying that x is now sort of locked between a -3 and a 2. Good there, and let's see what, just to give you a reference here, I'm on page 116, since some people are flipping through the textbook trying to find it here. 116 is where I'm at. Okay, so a few things we've got to notice here is, notice all these inequalities are all less than symbols, less than or equal to. What you're really saying is this: you're saying that -3 is less than the number that I want, and the number that I want is less than 2. See how when you say it, that little x is sort of caught in between them. Okay, so in these guys, it's always going to be either a less than symbol or a less than or equal to symbol. So -3, less than or equal to x, which is less than or equal to 2. So x is caught between this one, and I want to include the -3, I want to include the 2, hence the brackets. This one, notice I only want the -3, I don't want the 2. So -3 less than or equal to x, which is just less than 2. So interval notation, and there's my graph. Sometimes I just want to include the number at the end. So I just want the 2, not the -3, so there's my little symbol there. So 4 different sort of kinds of ways to write something that's sort of couched in between. Again, not even going to look at the open dot, closed dot stuff, since we sort of moved beyond that already. Okay, now this one, this is called the short notation for and. That's what this is. But before we get there, let's just do the basic or statements and statements, and we'll see how this sort of fits into it. So number 4 and then number 5, easy graphs. And again, with number 4 and number 5, we're just sort of getting the concept here. Once we get the concept, then we'll actually do some problems here. Just want to introduce the concept. So we say x is less than or equal to 3, or x is greater than 5. So here's what we're going to do, just so we understand it here. Let's graph this whole concept here. X is less than or equal to 3. So I make a little graph. I put a 3 over here. And x is less than or equal to 3. What do you guys say? Is that a bracket? Is that right? Bracket going to the left. And then we're going to graph the other one underneath it here. So this one's going to be a 5. So we're going to make 3 graphs by the time we're done here. X is greater than 5. Graphing that, let's see, bracket or parenthesis? Okay, parenthesis, all right. Parenthesis going off to the right this time. Okay, what does the or statement mean? It just means that when is it at least true for one of the graphs? Right? When is the double-double true? When is the cheeseburger true? It doesn't either or. So as we write down our final graph, this one's going to actually include this top graph over here. Right? It's true at 0 for the top graph, right? If we say is 2 a part of the solution, yeah, part of the first solution. Is 2.5 true? Yeah, it's part of the first solution. How about 4? Is 4 an answer to these? No, it's not true for this one, and it's not true for this one, therefore it's not true for the total. Okay? 5, well, 6. Positive 6 is true for the second inequality, so therefore we're going to have that is our answer. I'm going to just sort of let it sink in just for a little bit here. So the or statement says if any one of the equations or inequalities is true, therefore it's going to be listed as a final answer. And the or statement usually what it does is sort of there's a gap in the middle and it goes off 2 different directions. And then we also have, of course, interval notation to represent that. So let's see how we're going to do this here. There's kind of 2 different pieces, right? There's this piece, and there's a gap in between. So how do we write that in interval notation? We go like this. We start off negative infinity. And we go up to 3 with a bracket. So that's this first part here. And then the question is, how do we account for this little gap? What we do is we put a little u, and that just means union, which technically just means or from 2 slides ago. And then we set up this graph here. So parenthesis 5 comma positive infinity and a parenthesis. So notice, so we're saying the answer is 3 or lower or anything that's bigger than 5. So or statements typically have this little gap in the middle and they go off 2 different directions at the end. The and statement, a little bit different. Let's take a look at this one here. Let's graph this one. Let's graph this one. Let's put it together with an and afterwards. Now the and means both have to be true. So x is greater than or equal to -3. Let's graph this guy. Put a little -3 over here. Let's see. Let's make 3 graphs right away since we're going to do them anyways. -3. Bracket or parenthesis? Going off to the right because we're going greater. X is less than 2. Let's put a little 2 on our second graph. Let's see, bracket or parenthesis? Parenthesis going off to the left. Make arrows as well here just to make sure that we got it here. Arrows there. Arrows there filled in. Okay, so and means I need both of them true at the same time. So let's look at our number line down here. If I'm looking at like -5, is the number -5 true for both? Nah, it's only true for the bottom one, right? -4, is it true for both? Just the bottom one. Okay, how about -1? Yeah, it's true for both. It's almost like if you were to crunch these both together, it's wherever they meet. That's where the and is. So let's go -3 all the way to 2. We've got a bracket at -3. We've got a parenthesis at -2, and the and statement just means I would just want the stuff in the middle. And typically that's exactly what an and statement does. It's all the stuff in the middle. All right, how do we write it as an interval notation though? Here it is, -3, comma, 2, parenthesis. Okay, so number 4, number 5 done. We sort of looked at this whole concept of them. So now let's start working with it here. I think we're just going to look at the and statement and the or statement here real quick here. All right, I want to show you a little something beforehand. Notice this little interval notation is -3 to 2. This guy, seen this before anywhere? Jump back to here. Hey, look at that, -3 to 2. Isn't this the same thing right here? So eventually, and statements, what they become really is -3. I just want to show it to you real quick here. There's my and statement. So and statements really have a short notation to them. This is what we call a short notation. And whenever you can place an x sort of in between two different amounts, we got ourselves an and statement. So the short notation, let's work with the short notation then. Number 6. So -4 is less than or equal to 3x plus 2, which is less than or equal to 11. All right, let's go for it here. So notice there's not just an x in between, there's a 3x plus 2 in between here. So how do we work with short notation for and? Here it is. We're still trying to get this x by itself. But we're going to do this here. We're going to subtract 2 from the middle, but notice there's actually 3 sides we're working with, is that right? There's the left-hand side, there's the middle, and there's the right-hand side. So what we're going to do is we're going to subtract 2 from each of those sides. So, -4, subtract 2 is -6. Less than or equal to, now we have just a 3x by itself. Less than or equal to 11 minus 2 is a 9. Perfect. What should we do next? Divide by 3 and all 3 sides, right? And we got ourselves -2 less than or equal to x and less than or equal to 3. Cool. There it is. I'm done with my answer. It looks like I just need a graph. And can you give it to me in interval notation? Would you say bracket, right?
Yeah.
Okay, cool. Graphing -2 with a bracket, going to 3 with a bracket, and everything in the middle. And interval notation says bracket -2, 3, and so this is called the closed interval because both sides have brackets in them, and you're including both endpoints. The example in your book is an open interval, where they basically just have, you're not including the endpoints, you're including just the stuff in between. Those are called open intervals. It becomes very important in calculus when you see open interval or closed interval. Some things that happen because of that. Okay, but let's go with a typical or statement. Can we go from beginning to end? That's what I want to see. So beginning to end, can you solve this? Solve the left-hand side of that or statement. Solve the right-hand side of the or statement. Graph it and then give it to me in interval notation. All right, let's go for it together. So solving, I guess we should solve one side, and we'll solve the other, and then we'll put it all together here. So just solving the 2x minus 1 less than or equal to -7. I'm going to add 1 to both sides. Gets you 2x less than or equal to -6. Divide by 2. Since we're dividing through by a positive number, right? We're dividing through by a positive 2. You don't have to switch the inequality. So I got x is less than or equal to -3. Or, let's go back up here.
Sorry.
Start doing this one here. Let's see. Add 1 to both sides. Gets you a 2x greater than or equal to 8 this time. Divide by 2, divide by 2. And how about we wind up with x greater than or equal to 4. Good there so far? Now the graph of this will happen like this. And again, you could put, let me say it like this here. For the or statement, it's easier just to do one graph instead of all three, because you know you're going to graph one side, you know you're going to graph the other, and you're done. So with the or statement, -3 is here. Bracket or parenthesis? Bracket. Yep, to the left. And then 4 bracket to the right. And then you have a final answer of -infinity to 3, bracket union, bracket 4, off to positive infinity. All right, out of curiosity, raise your hand if you got at least to the graph. You got at least to the graph all correct before I gave you the answer. Cool, all right, about 60% of the class. That's not bad. All right, last two problems here. Of course, they're word problems here. Where do we sort of use this stuff? So a company that manufactures ink cartridges for printers finds that they can sell X cartridges per week at a price. Here's your formula. X is equal to 900 minus 60p. Obviously, the higher the price, the less they're going to buy. So what price should they charge for each cartridge if they want to sell at least 180 cartridges per week? All right, and again, you have to think about this whole concept of at least. What does that mean? And so let's see. At least a person is at least 3 feet tall. What does that mean? What inequality is that? At least, would that be greater than or equal to, right? So you say, oh, I know, at Disneyland, right? It says you must be at least 48 inches tall to ride this ride. That means you're exactly 48, you can still ride it. If you're 50 inches, definitely you can ride it. So that at least part is really a greater than or equal to symbol. Right, and then if your kid is like 46 inches, you give him like bigger sneakers to stand on. Like, yeah, we can go. Okay, there's another one here, which you guys will see on the homework here. At most. What does that mean? At most. It's the other symbol, right? At most, even though kind of funny, the wordplay in English here. That means if you say at most you can have 4 watermelons. you're really talking about, you can have 1, 2, 3. You can still have the fourth one, but no more than that. Okay, so let's try to put this into symbols now. Let's see here. So what price should they charge for each cartridge if they want to sell at least 180 cartridges a week? Tell me if you think this is true. I'm going to write just X here. X is the number of cartridges, is that right? That has to be at least 180. Good there? And notice what we're going to do. We do have an equation because we're trying to put in terms of price. We do have a equation that says X is the same thing as 900 minus 60p. So we're just going to substitute this for the X. So 900 minus 60p now it becomes the X value, which is greater than or equal to 180. And you guys get to solve it. Alright, I'm going to start this as well here. So how about, first of all, subtract 900 from both sides. That goes away, leaving a negative 60p is greater than or equal to, let's see, 180, subtract 900, negative 720. Divide through by negative 60, and again, that big alarm goes off in your head, right? We're dividing through by a negative. Switch the inequality. Negative divided by negative is a positive. And then the zeros here at the end, we can just get rid of the zeros, right? That's gone. So 6 goes into 72 12 times, I heard. Perfect. Okay, so what price should they charge for each cartridge if they want to sell at least 180 cartridges per week? Limits. Kind of funny is the answer here. I'm going to think about this here for a little bit here. Oh, sorry. Let me go back to this here. So they should charge at most $12. Is that right? That little P means P is less than or equal to 12. Since the sign flipped, yep, it changed the other way now. Question?
In the question it says at least, and in the textbook it also says at least, and when it writes it down it says to sell at least as well. Does it matter if you say at least?
Okay, and number 9. Says there's a relationship between Fahrenheit and Celsius. If you guys don't know what that is here, this is the common way the two common forms of temperature measurement. Let's see, we use Fahrenheit in the United States. In the rest of the world, all the other countries in the world use Celsius. We just like to be different. We're just rebels at heart. So in order to get away from the British system, a long time ago, we developed our own metric system, measuring system. We developed our own temperature system, so we would not be like those British redcoats. And we sort of kept that ever since. There is also another one. There's a scientific measurement for temperature called the Kelvin scale, and that measures the movement of electrons inside an atom. Celsius, it measures the freezing point and the boiling point of water, and everything is constructed based upon that. A little bit less scientific, but still works. And Fahrenheit has no relationship to reality whatsoever. It's just the way it is. Okay, so let's see. The formula, Fahrenheit is equal to 9/5 C plus 32, gives a relationship between Celsius and Fahrenheit temperature scales. The temperature range in a certain day is between 59 degrees and 77 degrees. That's Fahrenheit. What would be the range in degrees Celsius? Ooh, we're talking about range here. We're talking about something starting and something ending. Is that right? And since we're talking about range, we're going to include the 59 and the 77. We good? Anytime you say is between, that means you don't include the endpoints. So if you say between, you don't include it. If you say range, then you do include the two endpoints. So 59 less than or equal to f, which is less than or equal to 77. Everybody good there? There's my range. My starting point is 59, my ending point 77, and that whole concept of less than or equal to. Except this is in terms of Fahrenheit, and the whole point is I don't want it in terms of Fahrenheit. I want this in terms of Celsius. So yes, we do have a relationship. 9/5 C plus 32. So 59 is still here, but let's convert that F into 9/5 C plus 32. Hey, I think I remember something like this. Anybody remember something like this? 3 different sides? What should we do first? Subtract 32. You got it. Subtract 32 from all 3 sides. All right, how about 27 over here? Now it's just 9/5 C only. And 77 subtract 32, how about a 45? Good there? All right. Now what should we do? How about this? Let's multiply by the reciprocal. That's probably the easiest, right? 9/5 over here. Multiply this middle by a 5/9. Will that work? It'll get rid of the 9. It'll get rid of the 5 at the same time. If we multiply the middle by 5/9, we're going to multiply this number here by 5/9. Also, we're going to multiply the 45 by 5/9. Third 15, that works, yep. And the 9 and 27 reduce, how about a 1 and a 3? And then 5 times 3 is 15. That's easy enough. Again, the reason why we multiply by 5/9 is to get rid of that middle. Let's see, 9 goes into 45 5 times. 5 times 5 is 25. And there's my range. So my range for Celsius, what is the temperature range in degrees Celsius? You can write it like that. Let me just sort of check on something here. How do they want it? Yeah, they leave it like this. So that kind of makes sense. The only thing we should put on here, we still should put still degrees here, because Celsius in terms of degrees, Fahrenheit is also in terms of degrees. As we do the problem itself, we really don't have to put the degree symbols in there, but once we get to our final answer, we should write it as in terms of degrees. All right, and that finishes up 2.4.